Good morning and welcome to our Power Quality Seminar. My name is Jürgen Blum. I'm the Product Manager of Power Quality of a-eberle in Nuremberg. I'm 53 years old and I'm working with the theme Power Quality since more than 28 years now. I'm doing this seminar together with my colleague Thomas Schwarz. We organize this seminar together. If you have any questions during the meeting, please use the chat function. Thomas and I will answer your questions directly over the chat function. So, I want to introduce you quickly our Power Quality support team. So first, it's me, Power Quality Product Manager. My colleague Ugo Yates, he's working in our team since 15 years. So he's absolutely a specialist about the product if you have any questions about our mobile analyzers. Manuel Polinsky, he's our specialist to analyze the data. So if you need service and you need help to analyze the power quality data of our analyzers, you can contact him, and we also provide professional service for it. He was working many years before he joined Eberle with our PQ-Boxes, and he was working for a company who designed filters and compensation equipment. And Thomas, who is doing the seminar with me together, he was also working with our mobile analyzers in his company before, and he also knows a lot about power quality. And Thomas is our specialist, especially for support and product training. Please give me some minutes to explain the difference between our mobile analyzers, and I want to introduce a little bit the difference and the features of our analyzers before we step in the power quality applications. We have a whole range of mobile analyzers, and all analyzers are a product family, and we are working with the same software. So if you can use one analyzer, it's easy to use all other analyzers because the software, the philosophy will be exactly the same. The using of the analyzers is really easy. So with all our accessory, we have a quotation in the plug, and with 2 pins, the box automatically detect and doing all the settings. So no setup is needed before you do a measurement normally. All our analyzers are 100% compliant to the important standard 61000-4-30, and all our analyzers comply to Class A devices. And inside this standard, there are different other standards directly linked, and for the interference of our devices, we are also here in the highest category for harsh environment. So the devices can withstand the highest transient and EMC fields. So we're getting more and more DC applications in our network to measure in solar plants and to measure in industrial environment. Therefore, all of our analyzers can measure AC and DC, voltage, current, DC power. DC, we can measure up to 1600 volt if you use face-to-face measurement. The current is only limited about the Rogowski coils or current clamp, so even 7000 amps will be not the limit. It depends on the clamps. If we install analyzers outside in the field, normally you do not want to use a socket, so it's more complicated. The easiest way is to supply the device directly from your voltage connector of your voltage leads, and therefore it's a must that the internal power supply should be also cut for and withstand the highest transients. So we can supply all of our analyzers with any AC and DC voltage from 100 volt up to 500 volt. So it's really easy to connect them. All of our analyzers are waterproof, so IP65. and for installation in the highest category in Cat 4, so you can easily measure directly at the transformer. For safety, all of our analyzers are protection class 2. So there's a big difference between fixed installed devices and mobile analyzers. I often see that people use sometimes a fixed installed device in a small cabinet and use it like a mobile box. So sometimes it's really dangerous because in our protection class 2, there's never any safety risk for the people you're using the analyzer. So if you do some faults and connect some voltage to the earth, to the green line of the analyzers, even here we can withstand up to 500 volts. You can do whatever you want. There's never a safety risk. If you do the same with a fixed install device, you have this voltage of the earth directly on your interface. So it's a risk for your PC equipment and also for the human who are using this. So be aware, there's a big difference between using fixed install and mobile analyzers if you do it in this way. With mobile analyzers, normally there's no risk because there's protection class 2. The device itself do not know what is the earth. Here two pictures of outdoor installations. So often utilities install our analyzers outside in the field, here on a pole mount transformer. Here's a PQ-Box 100 installed. We connect directly here the voltage leads, where also the power supply coming from, and the Rogowski coil. And we measure during heavy rains over weeks. Here's another application, is a PQ-Box 200 installed in overhead cables. Here we have isolated cables. We use the currents with Rogowski, and we have here the connector to take the voltage and even the power supply directly from the cable here to measure in overhead lines over weeks outside in the field. If you measure outside, we also have big temperature changes. So we have to measure even at -20 and up +60 degrees if the sunlight goes directly on the analyzer. So absolutely no problem. Only some slides to show the difference between the analyzer. So the PQ-Box 50 here was a main goal to our customer to produce the smallest class A analyzers we have. The size of the device was a must to make it as small as possible. Inside this box, there is a battery included, even the power supply, everything is included in the small box. Here's one picture with the application. So the cabinet's getting smaller and smaller. And for the most of our user, it's important that you can install the whole device with clamps, with Rogowski coils directly in this cabinet. We measure the voltage, even the power supply is coming from here. And with small Rogowski coils, we measure the current. So all-rounder is the PQ-Box 150, and here we sell the most of the pieces. The big difference to the PQ-Box 50 is a higher resolution. So in this device, we always use 24-bit resolution. So it's much more than 16-bit of the PQ-Box 50. And we measure the new range for supraharmonics from 2 to 9 kilohertz, which is also not possible for the PQ-Box 50. With the PQ-Box 200, we deliver more possibilities to the user. So additional to the for voltage and for currents input, we have a binary input. So for example, you have a big power plant and sometimes you have some disturbances. So either you can do all the trigger, you trigger on over voltage dips, or the easier way is to look which voltage you are losing or which voltage will coming during a disturbances. And you put this voltage to the binary input. And it could be any AC DC voltage you connect to the binary input. And we can start and stop the disturbance recorder directly coming from this signal. So every time your machine have some disturbances, the PQ-Box make a long disturbance record, and here is a must that you have a lot of pre-time, not post-time, because at the end you get a trigger with the disturbances, and you want to know what happened in the grid in the time before. The fifth current input can be used to measure the current on the PE or a differential current, or if you do not need a fifth current, then we can connect here a temperature sensor or sensor for sunlight radiation. We are really flexible here to connect any active sensor on the analog output. The PQ-Box 200 is the fastest PQ-Box we have for really fast transients. Here's the sampling of the PQ-Box is 4 megahertz. And if you want to detect fast transients, which do a disturbance to your devices, then it's a must that your input of the voltage channel must be as high as possible. So we can measure transient from plus minus 5,000 volt. So up to 10 kV is a maximum range we can measure transients. Here one application where we measure the transient on voltage L1 to 3 with a high sampling. So if the sampling is high, it's easy to detect the maximum in the transient, the maximum measurement points. I started the development of the PQ-Box 300 because I'm a member of the standard 61000-2-2. This is a standard who describes the power quality in public low voltage networks. And years before, we only have limits for the public network up to the 50th harmonic. Higher than 150 kilohertz up to gigahertz, we have the EMC standards. But between 2.5 kilohertz and 150 kilohertz, there was a gap in all standards and we have no limits. But nowadays we're getting more and more electronic equipment in our networks and we have disturbances exactly in this range. And with the IEC standard, now we have limits since 2018, and I developed the PQ-Box 300 specially to measure the range up to 150 kilohertz. At the moment, in the standard 61000-4-30, we discuss, because I'm a member of the standard also, we discuss how to measure the supraharmonics in the future. And there's a big discussion if we want to measure from 2 to 150 kilohertz in 2 kilohertz bandwidth or 200 hertz. Some weeks before, the standard makes a decision that in future only 200 hertz bandwidth is allowed. So we have to measure with our device from 2 to 150 kilohertz every 200 hertz bandwidth. So a lot of data coming. The PQ-Box 300 at the moment deliver both possibilities. You can select in the settings between 2 and 200 hertz because I know during the development there are 2 possibilities in the discussion in the standard. But in the next update, we skip the 2 kilohertz and only the 200 hertz will be included. So why do we need this? Worldwide, there's a trend, we have to save energy. So if we want to save energy, now all our equipment has to change to electronic. So it's higher efficient. We have lower weight, like here with a transformer. In an old PC, you have a lot of metal, a lot of copper, so it's expensive and heavy. And now you can fulfill the same doing with a switching power supply. So lightweight and lot of less material. Also light, change it worldwide to LED. And an asynchronous motor changed to a frequency converter controlled motor. So this is positive for the power supply, but negative for the power quality, because now a lot of things changed in our electric network. And I will tell some disturbances and applications about it. Here I see typical clock frequencies of typical devices we're getting in our network more and more. So for motors, we have frequency control drives. It depends a little bit of the size of your motor. If you have a big engine, then the sampling frequency of the frequency converter is low, about 2, 3, 4 kilohertz. If you have a small machine, then the sampling frequency is much higher than 10 kilohertz. Solar inverters, which we install at households in low voltage grids, they typically make disturbances with 16 or 18 kilohertz. So why 16, 18 kilohertz? We can hear noise and disturbances up to 15 kilohertz. And they put the sampling frequency a little bit higher than the frequency we can hear, because we install a lot of solar inverters in households. And if the sampling frequency would be, for example, 9 kilohertz, there's a big risk that all the people can hear this noise, this beeping noise of 9 kilohertz in their household equipment, for example. So wind farms, because they have a big power, there is a sampling frequency really low. Electric cars are in a wide range. I measured electric cars with the interference to the grid from 10 kilohertz up to 80 kilohertz. So there's a wide range, and you do not know before in which range, maybe which car will do the interference to your grid. Here's a small story where we measured the big motorway service station. So it's a big gas station, but they install more and more electric charger for electric cars. They also install a lot of solar plants behind the gas station, and to get a lot of power during the day, if a lot of electric cars coming and also charging the supercharger, they install more and more battery storage systems on this motorway station. Here we see a nice carpet coming out of the software, and here we analyze all the disturbances of all harmonics and supraharmonics over a time period of 21 days. So during the 21 days at this area, they install more and more batteries, charger, and electric charger. So black means there's no interference, no disturbances in our measurement data. And the color is moving from green to yellow to red. And this is a height of the disturbances. So the maximum disturbance we find here is about 1.7 volt with 18 kilohertz. Okay, we see here 18 kilohertz is a disturbances we find every day, every working day, every weekend, but not during the night. So here, this is typical. This is the interference of the solar plant. And if the solar plant here is working every day and bring an interference of 18 kilohertz to our network, then you also see twice of 18 kilohertz and 3 times of 8 kilohertz. So these are the multiples of your sampling frequency, which the solar inverter brings to our network. So at this time point, the motorway service area install more and more battery storage systems. And these battery storage systems produce at 17,000 hertz some disturbances. But here in this, you easily see at which time points they install which new equipment. And from here, we're getting more and more different disturbances. So if we want to analyze supraharmonics, the disadvantage is that you get a lot of data. And a lot of data you are helpless to analyze. You need a professional software with a lot of nice graphic tools to show you in all this data what is important. So this is one possibility to show a lot of data over a long period. The next possibility is a 3D graphic. With a cursor, you can move this graphic and look from all sides. And also here, the story is nice to see. Here we have the solar plant, and they install more and more solar inverters. So you see, our level goes up over the limits here in this network. And the motorway station have a lot of problems. They have a small supermarket. In the supermarket, they get problem and with the lights and yeah. At this time point, they install the battery storage and even the battery storage system to get the power of 50 Hertz and put it back to the network to buffer the network is power electronic. So you do this with a high sampling frequency to build from AC a DC or from DC and AC back. Here are the limits we get from the IEC standard. And for us as an engineer for electronic, it's not so nice because the standard works with limits in dB per microvolt. So from 9 to 150 kilohertz with limits for the public network, but the limit, the scaling is a logarithmic scaling in dB. So we have limits from 129 dB at 9 kilohertz, going up to 90 dB at 150 kilohertz. So here it's easy to see that if the frequency is increasing, the limit goes down. In our software, you can change the scaling in absolute values in volt or the scaling in dB per microvolt. So I prefer to work with absolute values, so you can change any bar graph, time level diagram, even the 3D graphic. You can select you want to analyze it in dB or in volt. Yeah, here also you see an interference from one device here, and this is 2 times, 3 times, 4 times of the disturbance one power electronic is providing to the network. Here many other frequencies automatically coming with. The use of our analyzers or any other analyzer you are using could be from Fluke, Tranets, everything. In power quality, it's a must. The frequency you want to detect, you want to measure, the analyzer must be sampled at least twice of the signal you want to measure. So this is an old PQ-Box 100. We do not produce a box, but many customers are working with the PQ-Box 100. This device has a sampling frequency of voltage and current about 10 kilohertz. So the maximum limit is 5 kilohertz to detect disturbances. The PQ-Box 50 and 150, here the sampling frequency is 20 kilohertz. So we can measure all of the disturbances in our grid up to 10 kilohertz. The PQ-Box 200 has a sampling of 41 kilohertz. We can measure up to 20. And the high-end box, the PQ-Box 300, have a sampling frequency of 409 kilohertz. And we can measure online up to 200 kilohertz and offline permanent up to 170 kilohertz. But 150 is a must because the standard provides limits up to 150 kilohertz. So here we have a real measurement in the public grid, and here a lot of customers reclaimed they have problems with electronic systems, electronic cooker that can't be switched on off during normal working days. On the weekend it's okay. And a lot of people reclaim that they can hear some noise during the daytime, but not on the weekend. So there is any industry customer with some frequency converter who is doing some interference to the network. And here in the lower harmonic, we see the typical harmonics. Additional to the harmonics, we analyze there's a 5 kilohertz, a 10 kilohertz, 15 and 20 kilohertz as a disturbance in our network. The highest value we can see is at 10 kilohertz with about 1.7 volt. So the most of the power quality analyzer are completely blind for this kind of disturbances. The most of the power quality analyzer nowadays measure only up to the 50th harmonic voltage and current. So, and here are the limits of our PQ boxes. So 150 can see the 10 kilohertz, but only the PQ box 200 can measure up to 20. This is one example of an electric car. Here I measured at the AC coupling point to a wall box, and I measured the interference of this hybrid car. It's a Mitsubishi Outlander. The Mitsubishi Outlander, if he charge from public grid, he's producing an interference about 50 kilohertz. And if the car is producing a 50 kilohertz, a 100, 150, 200 kilohertz coming with. So many additional frequencies will be also produced from this car. And maybe one of these frequencies is some disturbances for other electronic equipment because a sensor maybe is working with this frequency. So with the PQ-Box 200, we also can't analyze 50 kilohertz. So this box is blind for this. Looks like this. The picture before with a 10 kilohertz with 1.7 volt. This is an oscilloscope picture. And I make a snapshot in this grid where a lot of people have reclaimed as a utility with disturbances. And the first oscilloscope picture is made with a PQ-Box 100. So the PQ-Box 100 have a sampling frequency of 10 kilohertz. And if I'm doing the same snapshot, same coupling point with the PQ-Box 200, so we now see the high frequency which happened in this network. This is 10 kilohertz with 1.7 volt. So if the interference here in this grid would be 22 kilohertz, could be a high disturbances. So also the PQ-Box 200 can't see the disturbances. You have to be in mind that your analyzer always is blind at 50% of your sampling frequency. So in electronic, this is a Nyquist-Shannon theorem. So each analyzer must provide this. We need a big filter that we do not measure wider than 50% of the range of our sampling frequency. With a big, powerful software, we are working on our PQ-Box mobile software more than 16 years. So the high-end software delivers a lot of automatic reports, nice graphic views, and helps you to analyze what is interested to analyze in a big data. Because our analyzers always measure a lot of data. If you press the start button of a PQ-Box 150, for example, we measure more than 3,000 different parameters, and you do not want to analyze them all after your measurement. So you need a professional software that the software tells you what is interested in all this data. The software is completely free. You can install the software wherever you want, and even all updates, upgrades with new features are free. Inside the software, I implemented the most of power quality standards worldwide. We have standards, South Africa, IEEE standard, all IEC standards. As I said, I'm a member of a lot of power quality standards of the working groups. And if one standard changes some parameters, I do this for you in the software. You select which country, which standard you want to select, And the software provides you all the filters, barcodes, limits, especially for your standard. If you make long time measurement, there's also a big feature from our software. Even if you measure months, if you click with a cursor to the extreme values, voltage dips, swells, current peaks, you get an information exactly to 1 microsecond. So here's a voltage dip to 192 volt, and the software tells you, even if you have a long time data with 10-minute interval, you get the message that the voltage dip was at 3 hours, 70 minutes, 22 seconds, and 801 milliseconds. So the timestamp is exactly 2 milliseconds to each data, even you're analyzing only the online data. Another big feature from our devices is that we can have really long disturbance records. Here is a big 4 megawatt motor at an industry customer, and if a big 4 megawatt motor starts, it takes a long time. This photo is about 1 minute and 40 seconds, so 100 seconds the 4 megawatt motor need to start. And we not only measure the voltage dip and the current, we also have the real power, apparent power, reactive power on the basis of 10 milliseconds. And even the frequency or frequency change is done on the basis of 10 milliseconds. This is unique. You get a really long record, and not only voltage and current, like the most of competition, you get also all power frequency data on basis of half cycles. The long time of the recorder, you can tell the device you need the whole time as a pre-time before something happened. Here, this is one story where a big generator stopped during 1 week many times. And we want to find out what is the problem. So often customers take an analyzer and measure the power quality. Is there a voltage dip or swell or something with harmonics? Much easier is to tell the device, if the generator is working fine, we have 70 amps. And if the generator has some disturbances and stop, I take the current and tell the device, if the current goes lower than our threshold, lower than 50 amps, then we have a problem. Then I need 600 seconds before something happened. And now I'm analyzing, okay, what was the problem? And in this case, there was a really small voltage change and the generator reacts on it. But it's only a voltage dip of 2%. And no analyzer normally would recognize this with a threshold. Often you have plus minus 10%. So much easier is to trigger on a binary input, or I take the current. If something stops, I'm interested in a long pre-time to analyze what happened. Or in this case, I prove with my analyzer, I see that the generator stopped, but the network has no problem. And if the network not really have a problem, you get no trigger, often from other analyzers. To the fifth current input, which call it aux input, we are absolutely flexible. You can measure the temperature of your transformer with the harmonics or the load. You can measure the sunlight radiation at a solar farm, the radiation in watt per square meter to the load of the big solar farm. So any sensor, any active sensor, you can connect to our analyzers, and we even can trigger on temperature, differential current, so endless applications are possible here. Here's one example of a temperature measurement in a small cabinet outside in the field where our analyzers installed, and I was interested how is the heat during the summertime in Germany inside this cabinet, and we reach 55 degrees. Okay, that's normal, and our analyzer, as I said, are produced for a normal temperature, outside temperature up to 60 degrees. If you're using the aux input, you activate the aux input in our software, and here you have a wide field of different sensors. And if I tell the box I'm connecting a temperature sensor from -20 to 80 degrees, then in our software at oscilloscope AMS trigger, the aux input is also active, and we even can trigger on a temperature or differential current or PE current. So many applications are possible here. Now, one power quality story with supraharmonics where I used the fifth current input. There was a small photo studio, designer studio, a small own company in a big industrial area. And in this office, there was a RCD, and this RCD tripped many times a day. So the people can't work. So the electrician of the company want to find out what is the problem for the RCD. So in 99% of the faults is an isolation problem. So the electrician deconnected all devices and make an isolation test of all the cables. So all the cables have no errors, they're okay. Then maybe the fault should be one of the devices connected in the office. So they proved all the devices, and even no device have any isolation error. The next idea of the electrician was, okay, now I switch off all the fuses, and maybe I switch on only one fuse, and I look where is a problem to trip the RCD. During this test, the electrician recognized even if you switch out any fuse and no line is on, the RCD trip. And now he was helpless. He asked me to provide some service to measure power quality, and we want to find out what is the reason here to trip the RCD. And here is a nice story. It was supraharmonics. I connect my analyzer with a voltage, with a magnetic probes. It's really easy to connect at the fuses here or at the RCD. Really fast to connect L1 to 3 and neutral with magnetic. Then I connect L1, 2, 3 and neutral the current. I measure off the office, and with the fifth current, I measure the differential current, not the PE. I'm interested to see what is the differential current. It's the same value the RCD also measure and is tripping. So if the RCD trip, also in this constellation, I'm only interested in pre-time. I'm not interested in post-time. So the most of our competition have a long post-time, but only limited pre-time. As I said, our analyzer, we can look in a long time period what happened before we get the trigger signal. So here I've made an oscilloscope picture over 4,000 milliseconds. The RCD were tripping here, and with the software I'm analyzing, okay, on which current does the RCD trip? And we can analyze here in the FFT coming out of this oscilloscope picture, there's no big value on the 50 Hertz. So 50 Hertz is an isolation problem. But here in this constellation, on the current, we see only a 8 kilohertz and 16 kilohertz. So this RCD will trip on supraharmonics, 16 kilohertz. So where does the 16 kilohertz come from? Because we switched off all the devices in this office. In this office, there are a lot of cameras, monitors, PCs, LED lights, and in each of these devices, nowadays, we have in the input some filters. We have a switching power supply, and for each device, you have in the input some small condensators. So they're really small, and there's not really a big current at 50 Hertz. But the impedance of this condensator getting small if you provide a kilohertz on the voltage. And if this small condensator see 8 kilohertz, 16 kilohertz on the voltage, there will be a small current going from phase to earth and neutral to earth. At the time as the electrician switched off all the fuses, neutral and earth is still connected. So with the interference coming from a different company on this industrial area, we deliver to the voltage 16 kilohertz. The 16 kilohertz in the current going from neutral to earth, and the RCD, a 30 milliamp RCD, can trip beginning at 15 milliamps, have to trip maximum at 30 milliamps. So if you have 20, 30 small devices and each input condensator take 1 milliamp, then it's easy to reach the limit for the RCD, and the RCD is doing everything correct. He has to trip at 15 to 30 milliamps. In our software, we can also make snapshots online, offline, on the differential current here. This is a waveform. And if you have the waveform, in the software, we also have the FFT up to 20 kilohertz, and we analyze how does the current look like if the RCD is tripping. And here, I told you, was 8 and 16 kilohertz the reason for it. So normally, if you have different customers who producing the harmonics over the current going over your cable to the transformer. In the most of the harmonics, the transformer will transfer to the medium voltage network. Even in the medium and high voltage network, you will find the 5th harmonic, the 7th harmonic. So all the disturbances we normally produce mainly on the low voltage side. With superharmonics, this is absolutely different. So this was a building with a photo studio. So the photo studio was in the upper floor of the building. The whole building was connected to the public grid with a 400 kVA transformer. On the first floor of this building, there was a big protection factory, and they are using motors with frequency converter. And all the frequency converter producing some high frequencies with 8 and 16 kilohertz. And the 8 and 16 kilohertz on the current can be transferred with a transformer. If you look to the formula of the impedance of the transformer, you can easily see if you put in at the frequency here 50 hertz and calculate the impedance, or I insert 16,000 hertz, the impedance is huge. And therefore, it's not possible to transfer the superharmonics from low voltage to high voltage grid. So superharmonics normally will be never a big problem in medium voltage network, but it means they stay in the low voltage grid. So if this customer is producing the superharmonics over the current of his frequency converter, over the impedance, we see all the disturbances, 8 and 16 kilohertz on the voltage. And now this frequency is looking for a low impedance. The next low impedance he will find in all the devices of the photo studio. Each single computer, switching power supply, camera has a low impedance and getting a little bit of the current. And now the superharmonic can go here in a circle, so from phase and neutral to earth. So the superharmonic we generate here want to flow in a circle. Next story, where superharmonics could be interested. I did a research with a university together. It was a university in Bingen, and we invented a lot of people with electric cars that they can charge on one day for free at the university. And we try to analyze what are the interference of the different cars, of the different types of cars. And for us, it was interested, is there any interference between different electric cars if they charge every car on the same grid, on the same low voltage grid? Is there any interference between the cars? So we did this research with a lot of PQ-Box 300, some PQ-Box 200. So this was a connection. So at the university, we have 10 charging points. And you see, it was a big bus bar at the university. So the shortcut power is okay. So it's often in the public network much smaller. Here's a connection to the 20 kV network of the utility, and to the low voltage bus bar, the university also have installed a PV plant. So here is a nice Tesla, and for Tesla, the interference is typically also for new Teslas. If you measure a Tesla, Tesla is producing interference to the network with 64 kilohertz. This is typical for Tesla. 64 kilohertz is a high frequency, and most of the analyzers will never detect this frequency. Here, one other car is charging three-phase. We see on the current L1, 2, 3, on current is producing the interference, and over the impedance of the network, you see the same frequency, but smaller on the voltage. Here, maybe the blue one, you see it's not a perfect sinus. You see the same frequency which the car produces over the current on the voltage. Okay, this car is charging three-phase. If we analyze what is the disturbances this car produces for our network, we see on the current, if the car charged with 16 amp, we see 700 milliamp with 10 kilohertz. Over the impedance of your network, we see a voltage drop of 1.75 volt, also with 10 kilohertz. Be aware that at 50 hertz, your impedance is much smaller than at 10 kilohertz. So at 10 kilohertz, maybe in your normal low voltage grid, you calculate with an impedance of 5 ohm or 10 ohm sometimes. So a small current can produce a bigger voltage, and the voltage will be the problem for all other devices in this low voltage grid. Here we measure as a Mitsubishi Outlander. It's a hybrid car, and the car is charging only single phase. So we charge only on phase L3. So here with voltage L1, 2, 3, and only on L3 we charge the Mitsubishi. This picture I've showed some slides before. Okay, here we produce a 50, 100, 150, 200 kilohertz. So the 50 kilohertz interference here in the low voltage grid was about 350 millivolt. Okay. Now we connect more and more cars on the same parking lot here, and here the Mitsubishi Outlander is alone, and here the second car is charging. So the second car is charging, and the car is charging three-phase. You see on voltage red and green, because now we also have here some interference, and the Mitsubishi only charging on L3. So the Mitsubishi can't be responsible for these phases. So the reason here is a different car, and I go back, it was especially this car connected to the next charging point, produce this interference with 10 kilohertz to the low voltage network. All the interference which will be produced here can't go to the public grid and stays in the low voltage network. And now this frequency is looking for the next low impedance. And the next low impedance here only can be the next car. So here the waveform of the charging Mitsubishi looks absolutely different. So here's something wrong. The device reacts on it and stops after 1 minute. So it was not possible to charge the Mitsubishi all the time till the first car stopped charging. So over 3 hours, it was not possible to charge the Mitsubishi. It quickly stopped if you try to start charging, because the car recognized that something is not correct. Here the explanation is that the Mitsubishi is a low impedance for all the disturbance of the other car and get all the disturbances. Like we see here, car 1 is producing the 10 kilohertz. The impedance of the network is too high. It's not going in this. And now this current wants to circle here in a shortcut. And this is only possible over the impedance of the next car. And this car changed completely with this current and stopped charging. So what could be the impacts of supraharmonics today in our network? One is overload of switching power supplies. So a lot of people recognize that if they buy LED lights and the manufacturer say the LED light will last 50,000 hours. And a lot of people in industry recognize 50,000 hours, it's not possible. All the LED lights, the lifetime is much smaller. So what could be the reason for it? In any single phase device, switching power supplies of computers, monitors, or even in the socket of the LED light, you have exactly this. 4 diodes and a small condensator. So if the voltage in the grid is higher than the voltage of the condensator, the diode is switching through and the whole disturbances of the grid going to the condensator. So the condensator, if the diode switching through, see 50 Hertz and additional maybe 12 kilohertz, 24 kilohertz. So all the supraharmonics also going to this condensator. So this producing a higher current. A higher current is higher losses, and this means more heat, and more heat is always lifespan. This was a research of the University in Dresden. Here is a current of not a LED lamp, was a fluorescence lamp, and the normal current, half a sinus wave, is green. So if you deliver only 50 Hertz voltage, the current of the LED or of the light looks like this. And now they added some supraharmonics. They added a 2.2 kilohertz with about 3% on the voltage. And now the current looks like the blue one. So the current is much higher. And now the heat of all the lamps going up, here up to 5 Kelvin in this. So with only one supraharmonics, the temperature goes up. And if the temperature goes up, the lifespan goes down. So it's an easy explanation for it. And this happened to a lot of devices. The next problem which we could have with supraharmonics could be an acoustic problem. So people can hear between 20 to 16 kilohertz maximum. So the limit depends on how old people are. Younger people can hear a little bit more and older people a little bit less. But in this range, we expect that people can hear some noise. Therefore, some manufacturers try to put the sampling frequency of the power electronic a little bit higher, so that you never have an acoustic problem. But we're getting more and more of acoustic problems in our grid. Here in a small village, somebody installed a small hydro power plant. Here with a frequency converter, depending on the water here. And if they install this small power plant in the small village, we always see 12 kilohertz. The 12 kilohertz on voltage with about 1 volt will be delivered to all consumers in the low voltage grid till the transformer And a lot of people reclaimed that they can hear some beeping noise and LED lights in switching power supplies, monitor, a lot of beeping noise they can hear. And the utility reacts, and here the producer of this hydro plant have to install some EMC filters afterwards to limit the disturbances of 12 kilohertz. But first you have to do some measurements to see what is the problem here in this network, what is the reason that a lot of people can hear some disturbances. And the next problem, sure, the biggest problem is malfunctions of different devices. So in one also nice story, a big hotel installed in all rooms touch dimmer lamps. So you only touch the lamp and you can switch on and off your light. In this low voltage grid, a small industry customer is producing with a frequency converter some disturbances. And the disturbances, the multiple of the disturbances have exactly the frequency the touch dimmer lamp is working in this low voltage grid. And the production company was producing daytime and nighttime on all working days, not on the weekend. But even during the nighttime, it was possible that the industry customer switching on and off the lamps in a hotel automatically. So nobody can sleep here. So we're getting more and more supraharmonics in our network, and we can't provide it. It's a must. Only with electronic components we can save energy. On the other hand, we're getting more and more sensors in our grid, like here, automatic flashing toilet, a heating system with touch, or in industry touch panels. All of these sensors working with really small signals in a higher frequency range. And you can't avoid that there never will be any problem. So we're getting a lot of supraharmonics, and we control more and more with sensors. And there's always a possibility that we have a lot of malfunctions in special conditions in our network. So only some reasons to measure supraharmonics, and we're getting more and more of them. It's clear. I showed you the list of machines and devices who are producing this. Okay, the last 5 minutes I will invest to speak about how we can analyze with power quality analyzers who's responsible for the disturbances, who's responsible for the harmonics in your grid. And I see that people often try to analyze what is the direction of the real power of a harmonic. And the direction of the power of the harmonic should tell you who's responsible, who's producing the harmonic. And I will tell you why this is in 90% of the cases wrong. So, like at 50 Hertz, we can calculate the power with positive or negative with a sign out of voltage multiplied with current multiplied with the cosinus of the angle phi of this frequency. So we can do this with 50 Hertz, and we can calculate this also maybe for 100 Hertz. So the power of the second harmonic is the voltage of the second harmonic multiplied with the current of the second harmonic multiplied with the cosinus of the angle of the second harmonic. So an analyzer can calculate all of this. And if the phase angle phi goes from 0 to 90 degrees, this means we get the power from the utility to the customer. If this phase angle is bigger than 90 degrees, up to 230 degrees, this means that the power changed to a minus, and the customer deliver power back to the grid. So this is at 50 Hertz. If you have a generator or a solar plant, also with harmonics, this calculation is possible. So now we go to a real case. With a public grid, And in this public low voltage grid, we have a problem of the 7th harmonic. The 7th harmonic is too high. So we install a power quality analyzer at the customer too, which is a big production company. We measure here the current of the 7th harmonic. The 7th harmonic produce a voltage drop over the line and the transformer impedance of 0.57 volt. And now normally we expect to get the angle between the voltage drop and the current. So this angle is bigger than 90 degrees, and this means this customer is responsible, he is producing the 7th harmonic. But the analyzer is connected here. We only see what is the result of the 7th harmonic here of all producers of the 7th harmonic in this grid. Out of the medium voltage network, we always get the 7th harmonic. The transformer transfers the 7th harmonic one by one. From the public grid, we're getting 2.7 volt 7th harmonic. This customer, a big office maybe, is producing also the 7th harmonic with this equipment, but it's different equipment, therefore the phase angle could be in any direction. Our analyzer or any analyzer can only measure what happened here on the voltage. We can't calculate what is the voltage drop of this current. We see what is the result of everything. And especially the disturbances out of the grid will change from the amplitude and phase angle between daytime and nighttime. So it could be that this customer is producing 25 hours exactly the same, but the grid value is changing. And now your analyzer will tell you during the night you are positive, during the night you are negative. No, this customer is still doing the same. All other values will change the philosophy if it is positive or negative. So the direction of harmonics will be not possible. You can't use it if many customers could do harmonics. Only if your grid has only one consumer and the public grid has no harmonics, then you can use the direction of the power flow. But in this constellation, you do not need an analyzer. It's clear who's responsible. Anytime you need an analyzer to find out who's responsible, then it will not help. It's good that we have a lot of different devices, and all the different devices can produce the 5th harmonic, for example, in any angle. So electric switching power supplies, single phase, do often in this range, the disturbance of the 5th. Industry, big 3-phase frequency converter producing the 5th harmonic in this area. So both together for the grid is positive if you have this constellation. So the best way is you compare not the phase angle from voltage 5th to current 5th harmonic. So we compare what is a phase angle compared to the fundamental. It's much useful. This is a real measurement at the industry customer. We measure each cable, we measure the 5th harmonic. And if you add the 5th harmonic of all these different machines, we have a current of 190 amps. But if you measure the 5th harmonic at the transformer, you will recognize that the sum of the current is much smaller. So we, even the old PQ-Box 100, deliver the phase angle of the 5th harmonic compared to the fundamental of the voltage. So this is a basis. Now we can analyze that some of the producer of the harmonic, like here, are positive for the network and some are negative. So with this phase angle, you can imagine if you switch off this 70 amps of the fifth harmonic, the current of the fifth harmonic goes up. So this is a producer of harmonic, but if you switch it off, it gets more worse. So with this information, it's much more useful for you to look for solutions. So if we have here on this bus bar a problem with the fifth, I will analyze which here maybe some frequency converter we change from 6 volts to 12 volts converter because they do not produce a fifth harmonic. But I do this effort only where the fifth harmonic is negative. How we can detect the phase angle of two different frequencies is not so easy to understand. If you have a vector diagram, the fifth harmonic is 5 times faster than the fundamental. So how we can calculate a phase angle here? So our analyzers detect the phase angle between two different frequencies at the zero crossing of the fundamental. The fundamental of the voltage is a basis. And then we calculate the phase angle to this basis of all voltage harmonics and current harmonics. Like here, this is also a real measurement. Here, two different producers of harmonics coming together. We have some interference from office equipment. Here I can measure the fifth harmonic with 12.3 amps. Electric car is charging, connected to the office installation, and he also is producing some fifth harmonic with 9.2 amps. But our analyzer provides a phase angle. We know exactly where is the current at the moment. And if you add both, the sum for the transformer at the moment is only 5.6 amp. So if you switch off even one of these producer of harmonics for the transformer, it goes up. So with this information, we can work much more clear. And the last page I will show, it's live from our software. I go to the online software. So the angle of harmonics we produce online and offline. I connected here a PQ-Box 200. So I connect to the box. We need the online data. I need sure, we need some load. And we go to the direction of the harmonics. First, I only select phase L1. So here we have the basis. Orange mean this is a fundamental of the calculation. This is 0. And we see the third harmonic, the fifth harmonic, the seventh harmonic, the ninth harmonic. So all the harmonics coming here. We see the interference in the grid at the moment. So we have, I choose the fifth harmonic, 3.59 volt with a phase angle. So the phase angle is at the moment not so interested, but now I switched on a producer of harmonics. So here I have a big producer of harmonics. He's producing with 7.8 amp, also the fifth harmonic. But now we can easily get a feeling, is this machine positive or negative for the grid? So here is an interference in our network. And if I switch on this machine, he's producing 7 amps, but exactly 180 degrees opposite. So this machine will work like an active filter. So I go down. If I choose the 11th harmonic, for example, here we see the disturbance in the network on the voltage and the disturbance my machine at the moment is producing. And this is nearly the same phase angle. So if I add both angles and the result is bigger than before, then it is worse for the network. And if it is in this direction or here for the third and for the fifth harmonic, my plant, my device is positive for the network. So to work in this direction is much more clear nowadays to see if a producer of harmonics is positive for the network or negative for the network. My opinion is that nowadays we only get producer of harmonics. Each device which which has no sinus on the current is a producer of harmonics. And I'm only interested if I install many of them in my grid, is it positive for the network or is it negative for the network? So this is really deep in power quality. And if you are interested in this, go to our webpage. I've written a lot of technical articles, and one big article describes how to define the direction of harmonics. So it's an article about 8 pages. So if this was a little bit too short for you, or if you are interested, please send us an email, take contact to us and discuss this theme with us together. So I was speaking much longer than expected. So I will transfer to Thomas. And Thomas, please take the screen. Bye-bye.
Very much, Jürgen. I hope you can see my screen, and briefly you can also see my face. I hope so. If not, then this is not dramatic, since more important are the slides and the software I'm going to show you. So I have some webcam issues, but you have to excuse. So no problem. So I hope you can see my screen, my mouse cursor. And first of all, I am going to start with an example. I'm going to show you the PQMobil software. And in my first example, I will tell you something about an industrial area with a seemingly inconspicuous customer. So a small customer that, on first sight, didn't appear like causing big problems, but he did. So what was the problem? In our industrial area, there were a lot of offices, and they were complaining about light flickering, so a change of light density. So we asked him whether he could perform a measurement. Of course he did. He installed a PQ-Box 100. This was a couple of years ago, and he did a recording over 7 days. And I'm going to show you a few tips and tricks within the software. I will focus on the overview data timeline, as well as a standard evaluation for flicker. So every time you're confronted with flicker problems, I will show you a very nice and convenient way to get started. I will show you some tips and tricks regarding the scaling, the limits, and the markers in our display, as well as the minimum and maximum values. I will focus on that as well. I will mention some pre-selections. And last but not least, I will show you the 3 ways to get to your fault record. Each PQ-Box will record when there is something happening. So let's jump right into our software. So I will first of all go to my measurement data and select the measurement I want to show you. I will show you flicker and dips today. I will load everything, and here you can see the duration period was 7 days and 16 hours, so a week. This is always a good measurement durations because you see every single day during the week, you see weekends. And before I really go into detail, I will have a closer look on my overview data. So my overview data is this at the right bottom side, I will just focus in a little bit. You see oscilloscope fault records. You see the yellow boxes, green boxes, and you see small dotted lines, gray dotted lines over here, and you see a big gray bold line. So this line, the big bold line, indicates the night, so midnight from Sunday to Monday. So we see nothing happening on Sunday. We see something happening on Saturday, but less than on Friday or Thursday or Wednesday, Tuesday, and Monday. So first of all, I see, well, on Sunday, we didn't have any problems, any power quality problems. On Saturday, there were problems, but not as many as on Friday. So if I go with my mouse over here, we have a mouse over and it starts at 6:13 in the morning, and the last problem was around noon, so half the day. So before I go into detail, I just think of, okay, what could be a possible reason? So since there was nothing on Sunday, this is already a typical exclusion criterion for photovoltaic systems, because the sun doesn't stop on weekends, and we are not having problems on Sunday. So if there would be a photovoltaic converter that caused problems, it would also cause problems on Sunday. It would cause problems on 7 days a week. So we are looking for a customer who runs his business 6 days a week, whereas less hours on Saturdays. This is the first important information we are getting out of only the data overview. So this is a great way to look on your data if you want to get an overview and see what is going on there. The next step is I will go to this icon, norm evaluation, to get an overview of my limits according to the standard I've chosen before. And I want to see, okay, is everything fine or not? I see frequency is fine. The red bar indicates our measurement values, minimum value and maximum value, respective to the limit value. So this is all this display is normed to the limit values. And I see frequency, no problem. Voltage changes, no problem. But if I go on long-term flicker, I see, okay, long-term flicker, there were problems on phase 1, 2, and 3. So I will click on that, and that immediately opens me the timing diagram. First of all, I do a right click and select, okay, show me the whole week. 7 days, exactly 7 days. So the measurement started on Wednesday. I will see there was something going on Thursday, Friday, Saturday, nothing on Sunday again, and Monday, Tuesday, and Wednesday. I will display some limit values. With a right click, I can add the limit line, and this immediately adds me the proposed limit line of the standard I've chosen. So in this case, IEC 61002-2. I will open it and see, okay, the limit is at 0.8. Long-term flicker doesn't have a unit, so there's actually just 0.8, no amps, no volts, nothing, just 0.8. And I see the long-term flicker violated the limit value a lot. So now it's time to find out the cause. Let's investigate the permanent record data. So first of all, I go to my permanent record over here, and I will select the voltage. I will select the RMS value of my voltage and the RMS value of my current to just get a first impression of, okay, what could be the possible cause. And of course, I will also select the flicker. This can be found over here. The short-term flicker is a bit more accurate than the long-term flicker. And I go to timing diagram. Oh, excuse me. Because we were complaining about long-term flicker, I will select long-term flicker and I will explain the short-term flicker in a few seconds. So I open the voltage, the current, and the long-term flicker. And here I can see, okay, every time the customer ran his business, there was some current we measured, and the long-term flicker raised again. So, but when I zoom in here a little bit, I just click and hold the left cursor of my mouse, and I see, okay, there was something going on, but yeah, it doesn't seem really dramatic. We have maximum values of around 50 amps, and I know that the customer had a main fuse in this entrance rated for 63 amps. So there shouldn't be a problem, right? But if I know that from a physical approach, flicker is caused by quick voltage fluctuations, which in turn are caused by great current changes. So within the 10-minute RMS value, I cannot really see these fluctuations. So I want to go more into detail. I want to see the minimum and the maximum values of the voltage and the current, as well as a higher resolution of the flicker. So next, I will select my maximum values and my minimum values of the voltage. And I will also select the short-term flicker. So, and now I'm going to reveal the short-term flicker is a value that represents the 10-minute flicker value, and the long-term flicker in turn represents is calculated from short-term flickers, but represents a value of a time over 2 hours. So that's the difference. So minimum and maximum values of voltage, and I will also display the maximum values of the current. I will neglect the minimum values because that's not interesting to me. I want to see the maximum values. And with the maximum values, I get the 10 milliseconds. So this is the so-called half period RMS value. I will get every 10 minutes a new one, and this records the highest or the lowest 10 millisecond value within my measurement period. So I will click on timing diagram, and now I will see something different. Here I see the voltage, and I see sags in here, so dips caused by higher currents. In the middle and the mid diagram, there's the flicker, short-term flicker, and in the lower diagram, I will see my current. So I will just zoom in here a little bit to get a better impression of the data. And I see, okay, now there was something going on. I have voltage sags and around something I cannot really see, but if I press the shift key and do a left click in here, I can set a marker. I can also do it by right click and set marker 1 or 2, but I now set a marker with a shift key and a left click. If I press the control key and do a left click, I will set a second marker. So this is for marker 1 and 2, and I can see the immediate marker that is set for curve 1, the minimum of 200 volts. And at the same time, I will set a marker 2 with control and left click to see a maximum value of the current of 441 amps. So that's slightly different to the 50 amps we've seen before. So 400 amps is huge. Like I showed before, with the zoom, I can drag the window from left to right to zoom in. And if I want to zoom out, I drag the window from right to left to zoom out. So here I can see the exact time stamp of my current. So for example, my maximum value of 441 amps was at 6:23 in the morning and 11 seconds and 194 milliseconds. At the same time, there was a minimum on phase 2 of the voltage. So this high current obviously causes a voltage dip and voltage fluctuations. So to make life easier for you, we included some pre-selections. So you don't have to choose all the values by yourself. You can simply click on the selection at permanent record and go to long-term flicker. And then everything that is important is pre-selected. Just click on timing diagram and you have the same I did before manually. You see the maximum values of the current. You also see the RMS values of the current. And you see the minimum and maximum values of the voltage and of course the flicker. I will zoom in again. And here you can see a tremendous difference of, for example, if I just hide all the voltages and flickers. I can see a tremendous difference between the 10 millisecond maximum values and the RMS values. So if we just have a look at the RMS values, we expect, okay, 50 amps at around below 50 amps, that shouldn't cause any problems, but the maximum values of 400 amps, that's critical. But even though they don't cause the main fuse to trip, because our RMS values are still at around 50 amps. So here I can see the exact timestamp, of course, and each of these voltage dips I can see here. Of course, this is around 205 volts. This is not 230 volts anymore. Each voltage dip creates an event with a fault record. And now I'm going to show you 3 easy ways to get to the desired data you want. So first, I can click on, or I can again focus on the overview data, and I could click on, for example, the green marker over here. There's a half cycle event, so the 10 milliseconds, and the trigger is supposed to be a dip on voltage on phase 2. So I will just click on that and it opens me a timing diagram. I have my trigger line in the white vertical line here. If I don't want to see that, I just click on trigger line to make the line invisible. I can zoom in a little bit and I see the voltage on top and the current on the bottom. Sometimes it opens the graphs. So for example, with the not separated windows, and then I can just click on separate the windows with a right click. So if you want to see voltages above and currents below, if you have more than one unit of your values, you're able to separate the windows. So now I can see the fault record, and I can also jump to the connected oscilloscope fault record within here. So now I see the voltage and the current in one diagram, but yeah, there are too many lines. So I right click and click on divide axis. Now I get a better overview, the voltage and the currents. So this, for example, happened when a machinery was turned on, and we have currents that are tremendous. So the rush-in current, and this caused, obviously, a voltage sag. So this is one way to get to the fault record by the overview data. The second way is I have a list on my left window. I have different tabs for permanent record. I used before oscilloscope, half cycle, and PQ events. And the bottom three ones are for our fault records. For example, I go to the half cycle, and here I can see a list of my half cycle events. I'll just display a little bit more. And now I'm able to filter. So I can click on the minimum voltage, and I can sort everything I want. So I could sort by date, by time, by minimum or maximum voltage, and I could also sort by the maximum current, ascending or descending. So I will select minimum voltage ascending, and to get the lowest voltage dip with 189 volts. By clicking here, it opens, it displays the fault record, and I can simply run through all of the items in the list by clicking the arrow down and arrow up symbol down here, and it just opens me all the fault records. It's a very convenient way to see what was the most severe dip, for example, or the most severe current I had. So if I select the maximum current, that was the one with 441 amps in peak, I can easily select and filter everything within these boxes on here. So if I want to export this data, I can simply click on the printer symbol, and it opens me a window. I can print it out or create a PDF and hand it out to the customer so that he knows what is going on in his grid. And now I'm going to show you the third way to have a look on the dips and swells, the events in here. If I click on power quality events over here, there's an ITIC or a CBMA curve. If I click on that, I get the very well-known ITIC curve, and I can see some dips over here, but also some swells. So they're all linked. So if I hover there with my mouse, it gets a little bit bigger. And if I click there, it opens me the fault record. Now I can see the list again, and I'm here with my overvoltage on phase 3. I will just zoom in a little bit. And now I can see all the data. I can select some details if I want to. So now I don't know what was happening there. I will show you some details on here. If you click on the detail box, you see the minimum, mean, and maximum values of all the data that is displayed currently. So if I zoom in here, it will show you the mean value around 18 amps on phase 1, 2, and 3. So something was running, the machinery was running on there. If I zoom in on here, it was around 6, 1, and 11 amps. So this was obviously when the machine shut down. You only need this when the scaling is that high and you cannot see a difference between this line and this line on the first sight. So this is a very convenient way. With this detail box, and here you see the maximum values and minimum and mean values. This could be very useful sometimes. So as a summary, the three ways to get to your, the three ways to get to your fault record. First of all, the overview data with the oscilloscope triggers and the half cycle events. Here on the left side, you can see the number of events that took place in each category. The second one is the list on the left side, where you can filter for the maximum values of voltage and current and the category, of course. And last but not least, the ITIC curve, which can be found at PQ events and then clicking on ITIC. So these are the three easiest ways to get to your fault records. So as a little explanation for the difference between the minimum, maximum currents and the 10-minute or RMS values. So no data will be neglected within our PQ boxes. If you have a maximum or minimum value, you will always get the exact timestamp in a 10 millisecond raster, of course. So I will show you one quick example. I will just open the current and I will open phase 1, 10-minute mean value of the current through phase 1 and the maximum values. So I will open a timing diagram and then I will see this. To show you the exact difference, I will just change the display to step style. So by clicking on here, we have different types of viewing everything. So we could use single lines. So now we can see all the different measurement values with little indicators. We can only see the indicators. And now I want to show you the steps. So here, for the average value, we see our steps for with the markers. I can set marker 1 and 2, and the time delta is 10 minutes. So a 10-minute mean value. Every 10 minutes, we will get a new mean value. But the maximum values, they are somewhere in between these 10 minutes. So this one, for example, is around the middle, whereas this one is more at the beginning. So the maximum and minimum values, they always have the exact timestamp. You can see this timestamp in here, for example. So this was the first example I wanted to show you, and I wanted to focus on all the different things. I showed you the overview of the data timeline, the standard evaluation for flickers, scaling, limits and markers, minimum and maximum values, the very convenient pre-selections we included, and the 3 ways to see the fault record. The next example I'm going to show you in practice is about a waste generation plant that bought a new crane system. So at first glance, new crane system looks good, but what was the problem? So after installing the new crane system, many switch mode power supplies in the power plant were destroyed. So they changed their, they exchanged their old crane system with a classic B6 bridge rectifier and replaced it with an active front-end inverter. So this is the difference, the current-wise difference. Here we see on the left side the B6 bridge rectifier with uncontrolled recharging of the DC link. So the current doesn't look very appealing to the eye in first glance, not very sinusoidal, and we got a THDI of around 40 to 80% or even higher. With the active front end on the other side, this looks more sinusoidal at first glance, and it looks quite good actually at first glance. So this is what the voltage in our 3-phase system looks like with a B6 classic bridge converter, a rectifier. So we have this typical shape we get with the peaks and hills in here. And the customer, since he had problems, he wanted to measure his voltage after installing the new crane system, of course, and he measured with our PQ-Box 150 with a 20 kilohertz sampling frequency, and everything looked fine. So where's the problem? Well, if you are familiar with measurement techniques, you may have heard of some laws that say that the sampling frequency must be at least twice as high as the signal you want to measure. So with our 20 kilohertz sampling frequency, we can only detect frequencies up to 10 kilohertz. So what if there would be higher frequencies? We cannot measure them, basically. So on next step, the customer asked us whether we could help and perform a measurement. So we came and performed the measurement with the PQ-Box 300. Our flagship has a sampling frequency of 409 kilohertz, and we can measure frequencies up to 170 kilohertz. So this is what it looked like on the oscilloscope with our PQ-Box 300. The left part looked very similar to the slide I showed before, but the right part, that is very interesting. So this was exactly when the crane system starts. So it still looks sinusoidal, but it has an obvious high frequency ripple on it. So now we want to see what is going on there. Before I jump right into the software, I will inform you what I'm going to show you. I will show you some standard evaluation of supraharmonics. I will show you how to easily edit the evaluation period, and I will introduce you, like Jürgen mentioned before, a 3D view of our supraharmonics. And very important, how to change the report settings, because in this case it was a bit tricky regarding the report settings, and last but not least, like the report comparison between the standards IEC 61002-2 for public grids and 2-4 for industrial grids and applications. So let's jump right into the measurement. I will close all the windows and open a new measurement. I'm going to show you the supraharmonics crane. I will load it, and we see it was a short measurement of about 1 hour and 19 minutes. Let's get started. So I will close everything. So first of all, to see what was going on there, I will just simply click on my beloved button for standard evaluation. This evaluates me the whole measurement. So all the measurement, every single data point of my measurement will be evaluated against limit values. And at first glance, I see, okay, frequency, there was something wrong, and supraharmonics. I will start with the easy one because I know how the measurement was performed, and I can see everything is fine. 50 Hertz. Oh, what was there? Okay, little spoiler. The dolphin clamp was disconnected because the PQ-Box 300 was moved, and the dolphin clamp on phase 1 just fell down and was reconnected a few seconds afterwards. So this was a man-made problem, not on purpose, but no power quality problem, I promise. So, but this somehow doesn't look very nice. So at first, I know it was around, in the end of the measurement. So I go to my overview data and select the right bar. I have an orange bar on the left side and the right side. And here I can simply change my evaluation period. I click and hold down the left cursor of my mouse and just move it over here, for example. So I shorten my evaluation period to around 50 minutes and click this refresh button. And now I have to do my norm evaluation again. I click on it and voila, here we go. The frequency is fine. I just close the other window. Frequency is fine. Everything around 50 Hertz. Perfect. That's what I want. But supraharmonics are still there as I expected. So I will click on my supraharmonics. This opens me the tab supraharmonics 9 to 50 kilohertz in my view. I see a lot of bars over here, and obviously the visualization in decibel microvolts. This is because the standards only provide limit values in decibel microvolts. So I see there were many supraharmonics above the limit value. But to get a clearer view of that, and a better way to investigate is to change the visualization to volts. By doing that, I see, whoa, there was something going on at around 28 kilohertz. So at around 28 kilohertz, I have a voltage up to 12 volts. And 12 volts is a lot. I can simply click on that, for example, to get a time diagram, but I can also have a look on this view by a heat map. So to get a little bit better visualization, I just open the heat map and I see on the timeline from Thursday to Thursday. Okay, obviously we measured only 50 minutes now. It was all on Thursday, not 2 days. And I see, okay, there was a heat map and around 28 kilohertz, there was something going on. Even more interesting, I will open the 3D view. So now I can, if you want to show it to a customer or to students or just for yourself to get a bit of better impression of what was going on there. The 3D model is quite self-explaining. With mouse click, so I hold down the right mouse, click it and move it, and I can simply move the diagram. I can scroll in and scroll out, but I don't want to see all the frequencies up to 170 kilohertz, so I can just filter and hide the higher frequencies. So the most interesting part is around here. I could also select time-wise if I want, and I can move around in here to see what was going on here. So this is a great way of visualizing all our measurement data of superharmonics. And soon it will be available for the harmonics as well, as a little spoiler. I will just reset it. We can also change the colors if you want. But now I want to see the timing diagram. So this was going on time-wise. If I want to prove that it was really the crane and nothing else, okay, I will just go to my voltage, open the harmonics over here, superharmonics, the average values, for example, and I select the 28 kilohertz. And as well, I could select either the current, for example, or I can also select the power. I just go for the apparent power and display it in one timing diagram. And here I see, okay, superharmonics, the 28 kilohertz every time. It was around 8 to 10 or even more volts when, as I promised, the machine, the crane system was turned on. So if you want to prove something and measure the current, you're always good to go with the current or the power. So now I know the cause, and now let's evaluate the superharmonics. So limit values are useful, and I selected for evaluation, for example, the IEC 61002-2. So now I could print out the settings, export in PDF, and hand it out to the customer, which in turn shows it to the crane manufacturer. Well, that's what we did. And the crane manufacturer said, okay, I was looking at the results, but you are evaluating according to the wrong standard. And he is right, unfortunately. The right standard for this industrial application would be IEC 61002-4 for industrial grids, and class 2 in this case for applications connected to the point of common coupling, or IPCs, so in-plant points of coupling. So we can simply do that. With our software, it is very easy actually. I can just simply change the report settings. So I will just simply go on Setup, and here on Report Settings, I will click that, and I see, okay, up to now I evaluated regarding to the standard 61002-2 for public grids. I can simply click on Load, and I will go to the upper folder, config record. So this is the standard path within our software. And here you can see settings for applications all over the world. I will select the 2-4, and as I mentioned, class 2. I will just open it. And at first glance, I see no difference, but I see, okay, there is no evaluation above 9 kilohertz. So this is because this standard is more than 20 years old. It's from 2003, and it only covers limit values for harmonics up to the 50th order. And it gives recommendations, so only recommendations for superharmonics from 2 up to 9 kilohertz. So of course we included these recommendations because any recommendation is better than nothing. So I just click on OK, and now I can simply do a re-evaluation, clicking by that, and voila, everything is fine. No superharmonics, no problem, everything is fine. I can even click on here, and what stands out, there is a tad missing from 9 to 150 kilohertz, of course, because there are no limit values. But this would be the appropriate standard for evaluating this. You can change your report setting for every measurement, even for old measurements with a PQ-Box 100, for example, that is older than 10 years, no problem. Really, no problem. The only trade-off is that if you change the limit values, I will show you. You cannot change the limit values for generating dips, swells, and interrupts, because this needs, so they rely on settings that are valid while recording. So like I said, the only trade-off is dips, swells, and interrupts. If these, you cannot change these thresholds afterwards, because they generate events while they're recording. So as a conclusion, on first step, when you are recording on site and you configure your measurement, I will just click on, for example, we included a very nice offline version. I click on offline. If you measure with a PQ-Box 300, for example, 300, you can simply click on load, and I would always go either with the default parameters, which are 61002-2 and EN50-160. I would always go with this one because this also includes our up to 150 kilohertz. So when measuring, at first step, I would always consider the whole bandwidth. With this method, you don't exclude certain frequency ranges in advance, which might be useful for later investigation. So measuring, please, I would recommend go with the 2-2, which provides limit values up to 150 kilohertz, because you can change your report setting afterwards, and you can always deactivate parts or omit measurement data of your original recording. So my comparison between 2-2 and 2-4 I explained, and one more slide just to get a better impression. We have, from this horizontal line represents our frequency in kilohertz, and we have classic rectifiers, the older ones, like a B6 bridge rectifier, which causes the 5th and 7th harmonics, 11, 13, and so on and so on. Modern converters and machines cause trouble within that range, and where higher frequencies are often caused by, for example, active front ends. So here I display the limits of the IEC 61002-4 for industrial power grids, which has limit values for the harmonics up to the 50th order, so 2.5 kilohertz, and recommendations for up to 9 kilohertz. But everything above 9 kilohertz is totally neglected. So our 28 kilohertz problem with a crane wouldn't even be considered in here. So that's why again, my recommendation for at the first step, go with a standard which covers the whole frequency range, for example, the 2-2. And now you're good to go and see all the disturbances, and you can evaluate against limit values. So without this evaluation, we wouldn't have been able to say, well, you have a problem with the 28 kilohertz. Okay, I hope my message is more or less clear and I could provide you some help and tips and tricks regarding the different measurements. If you have further questions or problems, or you want to have power quality measurement service my colleague could provide, feel free to contact us. We are more than welcome to help you and to support you. On the left side, you see our postal address. You can always contact us via phone, for example, or email, or visit our internet site. If you have problems with your software or hardware, we can also support you via Microsoft Teams, or we included in our software a help ribbon, which is very convenient to support you evaluating your data, for example, or support you when you have problems with TeamViewer. So we can look at your desktop, at your client, and help you with problems. So that's the end. And I hope you had a very good time listening to our presentation and our tips and tricks.